Okay, welcome everyone. And we're very happy to have Sumit Mukherjee from Columbia today. And Sumit will tell us about persistent exponent for Gaussian stationary process. And as usual, if you have any questions, please feel free to unmute yourself and ask your question, or you could leave a comment in the chat and I'll communicate to your speaker. Okay, Sumita.
Thanks a lot, Shankar, for the introduction, and thanks to all of you for joining in. So the talk that I'm going to give today is based on joint work with Naomi Feldheim and Ohad Feldheim. So before I begin, let me just mention that I guess typically there has been various versions of various ways these talks have been done. Like usually you guys sometimes have two speakers or sometimes have one speaker. So just to give you a highlight of what's going to happen. So this is so I've devised this as a one continuous talk. We'll see how the timing goes, but the rough plan is that I plan to cover bullet points 1 and 2, where I explain sort of the main question and give some background as to what is known, and a brief overview of our results in the first part, and I'll sort of go over a brief overview of part of the proof techniques in the second part. But we may need to sort of adjust times here and there. So with that being said, and also as Shankar mentioned, please feel free to unmute yourself and ask questions at any point in the talk. Also, you can ask questions in the chat and I'll try to monitor that as well. Okay, so let's jump right in. So this is the question that we want to study in this talk. You have a continuous time Gaussian stationary process, and this is what I'm going to abbreviate as GSP throughout the talk, and this is what the GSP stands for in the title as well, which is centered. So throughout the talk, XT will be centered. Since it's stationary, it doesn't actually matter if I put a different mean, because that just corresponds to a change in level. In the main paper, the main paper is in preparation. So in the hopefully it will appear in the archive in 2 months or so, but maybe sooner. But in the main paper, we work with a general level, but in this talk, we are going to work with the level 0. And so basically, I'm going to also assume that the mean is 0. The variance, it doesn't matter. I'm just going to take 1, even though during the talk, it'll change. The variance will change from time to time, but let's start with variance 1. And throughout the talk, I'm going to assume that my process has continuous sample paths. So that's the basic object of study. And so what we want to study is this persistence, so-called persistence probability, which is the probability that your process stays positive. You start as stationarity. So what is the chance? So it's not like a Brownian motion where you're starting at 0, but more like the Olmsted-Uhlenbeck, so as to say. And you start as stationarity and you ask, what is the chance that your process stays positive from time 0 to t, where t is a large number. So this is the question that we want to study. This is well defined because your process has continuous sample paths. This is a well-defined random variable, so I can ask this question. And so it's not that hard to say that if your correlation goes to 0, then your persistence probability, this quantity pt, will go to 0 as t goes to infinity. And there are examples to see that this is necessary. So if your correlation does not go to 0, then you can have pt not going to 0. But let's say that we are going to work in the regime, so as to say, where the correlation goes to 0, even though throughout most of the talk we'll not explicitly work with correlations. But let's begin with correlations, because that, I think, is how the topic evolved somewhat. And so what we want to study is what is the rate of decay of this quantity, right? We know that it goes to 0, and we want to know what is the rate of decay. In the type of examples that we'll study, the rate of decay will be exponential. So we'll try to know a bit more about what is the exponent. For most of the times, we'll not be able to say what the exponent is explicitly, but maybe we can say something about the exponent, maybe some properties, some comparisons, and so on. That's the hope. Okay, so what is known about this? So, a very classical and powerful tool in this area is due to Slepian. So it's called Slapianslemma, Slepian's inequality, starting in the, it was given in a paper in 1962. So roughly it says the following. So I'm just going to state it in the context of Gaussian stationary processes. So it's centered means mean 0, variance 1. Also, you assume that the correlations are ordered, right? So you assume that correlations of y are point by point larger than the correlations of x. And then you can say the probability that x persists is less than equal to the probability that y persists. So the process with higher correlations is also the process with higher persistence, right? So that's sort of a very useful tool, as you might guess. It's if you know persistence of one and do not know the other, you can use comparisons. In many cases, if you want to show existence of exponents, you try to sort of upper and lower bound the correlations by sort of approximations of the same correlation. That way you'll get an exponent, because if you know the exponent of the first one, if you can sandwich it between two things that you know converge to the same exponent, you're done. So these are a very powerful technique. And just as a comment, so in this talk, we are going to only focus on stationary processes, but Slapianslemma is much more broad. It applies for non-stationary Gaussian processes as well. You just have to compare correlations. That's pretty much it. Okay. So what is known is sort of focuses mostly on the case when your correlation is non-negative, right? So we are first going to sort of go over a bit of what is known. If you assume that your correlation function rho is point by point non-negative, it's always non-negative definite, by the way. So it's I'm just asking it to be non-negative point by point. So in this case, you can use Slapianslemma in the following way. So you want the process to persist from 0 to t plus s. So think of t and s to be any two positive real numbers. And then you have, so this is larger than the probability of persistence from 0 to t and from t to t plus s. This is because I'm comparing x to a version of x, which is independent in these two domains, right? So you sort of take 0 to t plus s and construct them independently. So this process has larger correlations than this the process which is independent across blocks, and therefore Slapianslemma applies. Here I'm using correlation non-negative, otherwise the comparison here is not valid. And that's pretty much it, right? Because then, okay, so there's one more step, of course. You go from t to t plus s to 0 to s, that's by stationarity. But that's pretty much it. This will give you that 1 over t log pt, this quantity is subadditive, and therefore this exponent theta rho, which I define with a negative sign, this exists as a number in 0 infinity. So think of pt is like e to the power minus theta t approximately, and this number theta, okay, I mean 0 infinity are usually not the informative cases, but at this point I guess both are possible. I'm going to rule one of them out soon. But this is sort of an easy consequence of this Slapianslemma. And so, okay, you can ask, can this exponent be infinite? And the answer is no, or at least under the, if you have a Gaussian stationary process with continuous sample paths, the answer is no. And that's to see this, we again sort of go back to Slapianslemma. So by the same argument that we use to show existence of exponent, we can say the persistence is from 0 to t. You can compare it from 0 to 1 over k, and now you have tk many blocks. K is any integer that you like. So this is a lower bound using non-negative correlations again. And so you take 1 over t log. This will be a common operation, 1 over t log, and then you get this is greater than or equal to k times this quantity. So if I take a limit over t goes to infinity, I want this quantity to not be minus infinity. So I want this quantity. So this has no t in it. So I want this quantity to not be minus infinity. So basically I want this quantity to not be 0. That's pretty much it. I want this probability to not be 0 for some k. That's it. If I find any k, I'm done, because it's a lower bound for any k. And so let's show that this cannot be 0 for every k. Suppose this is 0 for every k. So as I pointed out, if this is positive for some k, I'm done. Then my exponent is finite. But suppose it's infinite for every k. then this is what must happen. Then I'm going to take a limit over k goes to infinity. So by continuity of sample pass, this infimum will converge to x0 almost surely, but that's a contradiction because continuity, convergence almost surely will imply convergence in distribution, and therefore this probability that x0 is positive will be half, right, by symmetry. And as I tried to explain, everything here that I'm doing with level 0 works with other fixed levels as well. Varying levels is of course a different story, which we don't plan to deal with in the current draft. But any fixed level, things are fine. But okay, so we know that this is half, so this cannot happen. So that's it. So it cannot be infinite. So exponent is finite. So the other extreme, can it be 0? As it turns out, it can. So it's possible for this exponent to be 0, right? So it was shown in this very early paper in the 60s using Slapianslemma that if your correlation is non-negative, and there are some other mild assumptions, but mostly if the correlation decays like t to the minus alpha, I should have pointed out here that alpha is between 0 and 1. So minus alpha, where alpha is between 0 and 1, not alpha larger than 1. So then this exponent is 0. Actually, they give upper and lower bounds, but in this talk, I'm sort of only going to summarize the results in terms of the exponents, just to keep the answers clean. So much more recently, it was so their results were sharpened by this paper, which shows that the exponent continues to be 0 if rho t decays in a regularly varying fashion, and the integral is infinite. So you're allowed to take rho t decaying like 1 over t, log t over t. So other functions are fine as long as rho is regularly varying and it integrates to infinity. You still have the same conclusion. And sharpening it was shown in this more recent paper that this neat characterization holds for non-negative correlations again. So this sort of does away with the requirement of regularly varying. So it says that your exponent is 0 if and only if your integral diverges. Right? So that's sort of that. Right. So it can be, the exponent can be 0 or it can be positive. But okay, so this is sort of the characterization. Okay, so another question that one might ask is okay, so now we know that the exponent exists, and as I try to indicate, usually trying to get the exponent is difficult for most correlation functions that we know. We don't know the exponent. The only one that I think we know is Ohmschild-Uhlenbeck. Even if we change the correlation to be something like e power minus t square over 2, which is like the Gaussian kernel, even then we don't know a number, but we can say some things about continuity maybe. So the hope is that if you have a sequence of correlation functions and if they converge pointwise to a correlation function, then maybe the exponents converge. So that's sort of the hope, and that's sort of a natural question, I guess, right? I mean, in what sense do the correlations need to converge if you want the exponents to converge? So the answer, as you may guess, it's not always. It's like demanding weak convergence of the processes, and sort of the exponents converging is like demanding sort of a convergence of large deviation exponents, and so it doesn't always happen. But one can sort of give a very easy counterexample based on what we already discussed. So take two correlations of your choice, fix them. One is an integrable correlation, so non-negative. One is an integrable correlation, and one is not an integrable correlation, as indicated by the notations rho int and rho non. Okay, so these are two correlations or covariances. Doesn't actually matter, but okay. So take fix two of them. And then take this sequence. So most of the correlation or your covariance comes from your integrable part, but a small part comes from the non-integrable part. So it's a convex combination of these two correlation functions. So clearly rho k is not integrable, right? Because whatever part you put, you're going to not be able to integrate this part, and hence the whole thing. And therefore, by your exact characterization, theta rho k must be 0, right? So you know that theta rho k must be 0 for every k. But on the other hand, if you take a limit, so the limit of the rho k's will be this integrable part. The non-integrable part will just wash away, and then theta rho int will be positive, right? So you'll have a sequence. So you need a sequence of zeros to convert to something positive, which is not going to happen. So okay, so this fails. But this sort of also tells you maybe, or gives you an insight into as to how or what type of assumptions one should put if you want the exponents to converge. So essentially, what you want to do is you sort of want to say, okay, maybe the correlations converge pointwise, but maybe there's some sort of uniform integrability condition which says that if one is finite, the other one's, if one's finite, the other one is as well, and if one's infinite, the other one is as well. So maybe we want the integrals to converge, right? Integrals to be closed in some sense. And so sort of this is a result in that direction. This sort of captures that you do need some sort of condition which sort of takes care of this type of issues. Like you don't want one of them to be converging and the other one to not. Okay, the first one you sort of always need, or typically need. You want the correlations to converge point by point. So these sort of finite dimensional convergences, right? Your correlations converge. That means that your process converges in finite dimensions. Or any finite dimensional marginals converge. The second one is sort of designed to rule out precisely the problem that we discussed in the last slide. Your correlations decay in a uniform manner, uniformly integrable manner, right? So your correlation divided by t to the alpha for some alpha larger than 1. You take a sup over k, the lim sup go is finite. So basically it says like, okay, your correlations are bounded by some constant times t to the minus alpha. So you want them to decay in a, I think that t to the alpha should go here. Sorry, I think that t to the alpha should be in the numerator, not in the denominator. So correlation is bounded by constant times by t to the alpha as t goes to infinity. So you want your correlations to sort of decay in a uniformly integrable manner. And the third one sort of is needed if you're working with continuous processes. You don't need this if you're working with discrete processes. All the questions that I pose here, there's a discrete version, and all of these results apply with slight modifications in the discrete case as well. Usually the modification is that you require less conditions. But in the continuous case, you require some sort of conditions to guarantee that your processes are tight, because of course finite dimensional convergence does not imply convergence of the process in C01 or C0T. So this sort of condition demands that these are tight. These are sort of the best known conditions in literature. So this is we don't have to remember this exact condition, but we need some sort of conditions to demand that the process are tight. So the way that I guess one can think about this. One can think about this B and C is B sort of put some condition on the correlation at infinity, and C put some sort of condition near 0. And that's going to be the theme. We need some sort of condition for the correlation at infinity and some near 0. And even when we sort of move beyond correlations, there will be this two types of conditions coming into play, no matter what we parameterize this Gaussian process by, and which I'll talk about soon. And so, okay, so now sort of let's move to the question that I want to study in this talk. Suppose
may I ask a question before that? So
yes,
the theorem you stated, I mean, it seems you worried about only one side. Do you generally have some upper semicontinuity or something of this theta, okay? Or is it also possible that
yes. So I understand your question. Yes, it's true. If you have non-negative correlations, you can get one-sided continuity. It's if you do give me non-negative correlations, the only the upper so-called upper bound is where we need these type of assumptions. The other bound is for free.
I see.
So you can just say the persistence on 0 to t is greater than or equal to persistence on 0 to m, and then repeat it across blocks, right? Because by non-negative correlations, I can just make it. I can just separate the blocks out. Now, as soon as I can separate the blocks out, then I'm just talking about weak convergence. So conditions 1 and A and C will be enough. So I don't need anything of the sort of B. But for the other direction, I need to argue that when I decompose these things across blocks, then I do get some sort of independence, right? I am allowed to decompose at a low cost. And that's where we need this type of correlation bounds.
I see. Okay.
Other questions that I can answer at this point? Okay, so let's sort of continue. Okay, so now we sort of want to drop this assumption of non-negative correlation, which is where we know a lot less. So we don't even know, right now we are studying continuity of exponents, but we don't even know there is an exponent if you drop the assumption of non-negative correlations. So we don't even know something very basic. Even if it exists, it can be infinity. In the non-negative case, we argued that it cannot be infinity, but now it can be infinity. In fact, examples of this nature have been considered by many authors, including some members of the audience. And so let's give one concrete example just to explain what can go wrong. And this would be, or modifications of this would be a recurring example in this talk. But let's take this simple process constructed by just two independent Gaussians. So take Z1, Z2 independent Gaussians and just set xt to be Z1 cos t plus Z2 sin t. Then this will be stationary. Okay, so you can compute the correlation function. You can see that it's in terms of t minus s. So you confirm that it's stationary. And now let's try to find out the persistence exponent. Now for this problem is very easy because I have to take this infimum of this quantity. Now, if I take this domain larger than 2 pi, then you're basically searching over all cosines and sines over the unit disk. And so if you do this infimum, there's a simple argument. You can characterize it in terms of r and theta, where r. So this is very easy to sort of compute directly. And this infimum is exactly the negative of the z1 squared plus z2 squared. In a similar vein, if you compute the supremum, it will be the same quantity with a positive sign. So it's sort of a direct computation, and that's pretty much it, right? So there's no dependence on t as soon as t is larger than 2 pi, and now you can compute whatever you want, right? So you know that log of the probability that your infimum is less than 0. Is just this. It's not going to happen. So it's minus infinity. So you don't even have to take a limit. It's just minus infinity for t large enough, where large enough is this. And therefore the exponent is infinite, right? So this is sort of a very simple example, but it just tells you that things can go wrong very fast. And like I said, this will be a recurring example in this talk. Okay, so let's try to give a more interesting example, which is of interest. So this is the so-called sync process, where the correlation function is sine t over t, interpreted to be 1 if t is 0. In this case, your correlation function is integrable, but not absolutely integrable. So you can integrable in the sense of you can take an integral from minus m to m, and then take a limit. Those integrals will exist, but not over, you cannot put an absolute value, and that's not going to be integrable. And so what is known about this example? For this example, we know that the persistence probability is bounded between two exponential terms. So C1, C2 are finite positive constants, such that this quantity is bounded between these two. We don't know that there is an exponent, right? And in particular, we don't know there's an exponent for any so-called non-trivial, the only example that I guess, there are very rare examples where we know the example, where we know the exponent. For almost all examples that I guess one can think of, we do not know the exponent. So one sort of approach which has proved to be fruitful is to sometimes think of the Gaussian stationary process not in terms of the correlation function, but in terms of the spectral measure. And so this arises via the so-called Wagner's theorem, which tells you that if you start with a continuous covariance function, then there is a measure whose Fourier transform is rho. which is, so basically this is what it means. You take your measure, you do a Fourier transform, and you get your correlations. So that's, and this map is 1, 1. Here mu is a finite measure. If you start with a process which has variance 1, mu will be a probability measure. But if you start with some other variance, mu will be a general measure. It will be finite, it will be symmetric about the origin. And also the converse direction is true. If you start with a finite symmetric measure, its Fourier will be a continuous correlation function. So one can potentially parameterize a Gaussian stationary process, and this has been done. And I'll point out some results which sort of which gives you very useful bounds in terms of the spectral measure. And just to give you an example, if you take the sync process that I described in the last slide, the corresponding spectral measure turns out to be something which could be interesting in its own right, which is just a uniform distribution minus 1, 1, right? So half times Lebesgue measure. So that's what happens for the sync process. In general, take your favorite mu, and you can ask the question, construct this correlation, and is there an exponent? The answer is most likely we don't know. It's almost always we don't know. And so what is known is sort of mostly from this paper by the Feldheims in 2013, where the authors give a general sufficient condition for exponential decay. So they say that PT is bounded between 2 exponentials. So the exact statement will come soon. If you assume the following conditions, there exists some beta such that positive, such that this mu has polynomial moments, and also your measure is regular, sufficiently regular near the origin. So your measure behaves, can be sandwiched between two multiples of Lebesgue measure in a small neighborhood around the origin, right? So this is sort of this dual type of assumption, right? So we need some assumption of the measure near infinity, and we need some assumption of the measure near 0. And it's sort of similar to the correlation assumptions. Usually assumptions on the correlation near infinity translate to assumptions on the measure near 0, and vice versa. So under these two assumptions, they prove that this persistence probability is bounded between 2 exponentials, similar to what was done for the sync process. And so what remained open after the type after sort of this, the work that I mentioned, or sort of all the literatures that I mentioned, is we don't know that there is an exponent. If I drop the assumption of non-negative correlations, we don't know that there is a sharp exponent. Even if the in any example, I mean, give me any example, we don't know it, or at least prior to the work that I'm going to explain, we don't know it. So a follow-up question is, if we do know that there's an exponent, can we say something about this exponent? Can we say something about continuity, or maybe finiteness, or positivity, anything? And so another follow-up question is, can we compare exponents, right? So this is sort of another question that one can ask. Says, can we do some sort of Slepian type comparisons? Slapianslemma allows you to prove existence of exponents, but it also allows you to compare between 2 exponents. And so we'll try to say whether it's an interesting question whether we can do that in the general case. And so this is the question. These are the kind of questions that we want to start. Yes.
One question. So you have these earlier assumptions on the rate of decay of the covariance function.
Right.
And now you have put the Feldheim's result has something on mu. So do these one give the other in some way, or?
Mostly yes, under some very mild. Okay, so correlations are integrable. So roughly, if you assume that the correlations are integrable, that means that the measure is nice near 0.
Okay.
So for example, if you start with a correlation function which is absolutely integrable, then the corresponding spectral measure has a density which is continuous everywhere. In particular, it is nice near 0. So usually assumptions near the way the translation works is assumptions near infinity for the correlation will translate to assumptions near 0 for the spectral measure, and assumptions near 0 for the correlation will translate to assumptions near infinity for the spectral measure. But they are very nice correspondences. Yes.
Okay, thanks.
Yeah. And so this slide concludes the first part of the talk. I'm happy to take any questions if there are. Otherwise, I'm going to move to the second part, which gives you an overview of the results.
Can you just show the statement of the main theorem?
Yes.
The main theorem that you showed.
The main theorem will come in a few slides.
No, the one that you showed before, that is when rho n goes to rho, theta rho n goes to theta rho. Ask your question.
This one.
Yeah, okay, very good. So now I had a naive question here. Now this may not make sense. Is it entirely possible that the exponents converge regardless of what happens to rho k? Are there examples?
There are examples that this is not true. So in particular, this would be an example, right? So take your
that I understand that doesn't converge, but I'm saying differently. I'm saying theta rho k goes to theta rho infinity, but rho k is doing something independently. Something they have no connection to rho infinity at all. Is that at all?
So you mean under weak? So the question is, can we make this the conditions of this theorem weaker? Is that the question?
For example, yeah, that's for example. Yeah. Are there examples that show this?
So there are slightly weaker versions of this theorem which does away with this t to the alpha. So remember, this t to the alpha has to go on top. This is my typo. So we have been able to replace these by slightly weaker conditions, but not too much. So there are counterexamples with alpha equal to 1. So we don't expect this to go through under much weaker conditions. In terms of in the setting of non-negative correlations, in the setting of in the setting of outside non-negative correlations, things are entirely open. I'll try to indicate what we currently know, but right. Well, not open. Okay, they're not open after the current work that I'm going to discuss, but these were open before we began.
Yeah. So just to repeat Shiva's question, perhaps. This convergence of exponents will not imply the convergence of correlation, right? That's what.
Yeah.
I see.
Point wise,
of course not. Yes, you can. So, for example, potentially you can have very different correlation functions with the same exponent, right? Because right.
Yeah, exactly. Very good. Yeah, very good.
I think that's what Shiva was asking.
Yeah.
Sorry. I misunderstood your question. So it's possible. So you can sort of parameterize a correlation in terms of some one-dimensional parameter. You can change it around. So you can sort of match two correlations you can match two very different correlations can just have the same exponent by chance. Yes.
Yes, that's precise. Yeah, thank you.
So can I just ask on the same question that I asked? You kind of answered it, but I want to, so the question about upper semi-continuity I was asking.
Right.
So if you go back, I mean, so for example, you give.
I cannot hear you.
In the slide.
Manju, I'm losing you. Maybe it's my connection.
No, it's on my side. It said, can you hear me now?
I can hear you now. Please continue.
So if you go back to the previous slide, you had non-integrable covariances converging to an integrable one.
Right.
So you cannot do it the other way if you assume the OKs are like L1 bounded, for example, right? I mean, so then Fatus tells that the limiting one will be. So yeah, what kind of example do you have in the other way where theta rho jumps down? I mean, that was actually what I meant to ask. Do you have?
So theta rho goes down. So let's see. In this example, theta rho goes. Theta rho will never go down. Let's see. If you have non-negative correlations, you can give this.
Yeah.
So this is the other direction is always the other direction always. So let's see. So theta rho k will be greater than equal to the persistence of rho k will be greater than or equal to persistence rho infinity. So lim sup of theta rho k will be always less than or equal to lim sup of theta rho infinity, always for non-negative correlations.
Okay.
So that's the direction which is free.
Okay.
The lim inf of theta rho k greater than or equal to theta rho infinity, that's the direction which is not free.
Okay. Thanks.
Other questions that I can answer? Okay, so let's sort of to the next section. Right. Okay. So so we are going to take an approach similar to the Feldheims in 2013. We are going to parameterize this Gaussian stationary process via the spectral measure. We'll sometimes utilize a connection between the spectral measure and the correlations, but mostly we are going to focus on the spectral measure. And so just to sort of set the notations, so mu is a symmetric finite measure on R, and whatever I'm doing on R, I can do it on Z, meaning we can sort of take a discrete time process as well. But in this talk, I'm going to focus entirely on R. So define its correlation function, rho mu, and now just take a centered Gaussian process with the Gaussian stationary process with this correlation functions rho mu, and I'm going to index it by x mu as because I want to study its effect in terms of mu, and now mu will keep on changing. So we'll sort of change mu from from line to line, and so x mu this notation is supposed to capture that. And so I want to study this persistence probability Pt mu, which is the probability that this x mu t process persists. And so this is the main result. This exponent theta mu, which is a negative 1 over t log Pt mu, exists, and it's a number between close 0 open infinity. Remember that it can be infinity in general, but so there must be some conditions. So one is that there is a finite log beta moment. So we sort of replace the beta moment assumption by the log beta moment. And the second is mu prime 0, which is this limit of, I'm not assuming that mu has a density with respect to Lebesgue measure. So mu prime 0 is just this limit. So mu of minus epsilon epsilon divided by 2 epsilon. Take a limit. This limit exists exists in this as an extended real valued number. So these are the two assumptions. Under these two assumptions, you will have an exponent. And I'll try to convince you that these are pretty mild assumptions as we go on. So, but just to sort of comment on the type of assumptions that all these theorems put, typically there's an assumption near infinity, which is sort of this one, and there's an assumption near 0, which is this one. So again, there is this dual type of assumptions coming in. This will be sort of and sort of we'll use the names A1 and A2 throughout the talk. Okay, so let's try to comment a bit on positivity and finiteness, just so we get a better understanding of what's going on in the general case. So assume A1, yes.
Sorry, about the statement you had, you allowed this derivative to be even infinity here. But even for that exponential upper and lower bound, you had a condition that of upper and lower bound by finite numbers, right?
Right, and that will follow in the next slide.
Okay.
So we'll give, we'll not give if and only if, but under some, okay, so we'll give sufficient conditions. So assume A1, meaning assume the log beta moment. And then, so the question is, okay, so can this be infinite? Well, if mu prime 0 is infinite, then the exponent can be 0, right? So that's one direction. If mu prime 0 is finite and mu has a non-singular component somewhere, it doesn't need to be at any specific place or near 0 or anywhere, but mu has a non-singular component somewhere, then this exponent is positive. So if you're allowed to assume that mu has a, let's say, non-singular component somewhere, let's say mu has a density, then this is an if and only if characterization, right? So if you assume that mu has some absolutely continuous component, then mu prime 0 finite or infinity determines whether your exponent is positive or 0. in the other direction, now we can ask about finiteness. So if mu prime 0 is positive, then theta mu is finite. And if okay, so the guess without we don't know an if and only if characterization here, but the guess is that if mu prime 0 is 0, then the exponent is infinite. And a very good result in this direction is in this paper by the Feldheims and Schaaf-Nitzan, is that if your measure on 0t decays like t to the alpha, so this will happen if you have a density which is polynomially decaying near 0, then your exponent will be infinite. Right? These, of course, not if and only if, but the guess is that so usually there are two types of things into play. Your mu, so just to summarize, if you want a non-trivial exponent, your mu prime 0 has to be positive and finite, and your mu has to have a non-singular component. These two will guarantee that you have a non-singular exponent. That's it. If you have a singular exponent, things can go wrong. I'll try to explain it in the talk what can go wrong with singular exponents, most likely in the second half. But right, so that's what we know at this point. Right, so there are sufficient characterizations. There's not if and only if characterizations at this point. But if you assume absolutely continuous component, we know a lot more. So okay, so what type of measures satisfy our conditions? So let me try to explain. Let me try to sort of claim that there's a lot of measures which satisfy our conditions. Just to start, for the sync process, mu is just uniform distribution minus 1, 1. This is compactly supported, so there's no problem integrating logs. I mean, you can take polynomial moments, doesn't matter, right? I mean, all functions are integrable. Any growing function is integrable. Also, another type of the other type of assumption is the one near 0. So you want mu prime 0 to exist, but in this case, mu has a density which is continuous and strictly positive in an interval near 0. And so the second condition holds as well. Like the limit is actually 1 or half, I think. The density is actually half. So the second condition holds as well. And so the two conditions holds, therefore the exponent exists and it's in 0 infinity because you have a non-singular component. Here the whole measure is non-singular. So the sync process has an exponent. So let's try to build more examples out of, okay, so you can take, like I said, you can take any measure, right? You can take a measure which is okay, so another example could be so you just need some nice conditions near 0 and some nice conditions near infinity. So starting with any if you're starting with any measure mu, if you truncate the measure, suppose you have a measure mu which is, let's say, supported on the whole line, you truncate the measure, then it's easier to satisfy the log beta assumptions. And it's also if you're nice near 0 for the original measure, you'll be nice near 0 with the truncated measure. So truncated measures also satisfy our conditions. Of course, if you start with the sync and if you truncate, you get sort of a smaller sync. But if you start with any non-negative correlations and if you truncate, start with a non-negative correlation, look at the measure, then you truncate, then the truncated measure will not have non-negative correlation. So now you have a whole vast of examples just by this truncation operation. And so that's one way to construct examples. More generally, take a function h which is a bounded non-negative function. You need some sort of nice conditions near 0 and h0 is positive. Again, you can relax these conditions, you can let h2 grow, so you can sort of play around a bit, but let me just give you some sufficient conditions here. Then if you construct this measure, nu, which is sort of a absolutely continuous with respect to mu, this also satisfies our conditions. If mu and nu satisfies our conditions, just to explain, the last example was with h, which is an indicator. If mu and nu are nice, then mu plus nu is nice, alpha times mu is nice, and if you scale mu down, and then that's also nice. So basically, mu of any set is, or mu of this measure of any set is mu of the same set divided by alpha. So you just sort of scale the measure. So that also satisfies all our conditions. If mu nu satisfies our conditions, and one of them is nice enough. So let's say a bounded continuous density. Then so does the convolution. Again, you can weaken some of these if you wanted to. You can let them to grow depending on the other one. In terms of correlation functions, this is a sufficient condition, but this so this says that if your correlation is absolutely integrable, then your conditions continue to hold. But this does not capture the sync process. So in terms of correlations, the results are not optimally stated here. Most likely one can do better, but this is the best version that we have currently in terms of the correlation function. But our results are much better if you use them in terms of the spectral measure. Okay, so just so I know, like, should I stop at this time, or how am I doing with respect to time?
Yeah, we could take a 15-minute break here and then maybe start again at 3:30.
Sounds good. So let's start again in 15 minutes. And I'm here. I'm happy to take any questions if there are any. And if not, I'm going to start from slide 21. Okay, let's begin where we left off. So this was a theorem statement, just to sort of go one slide back where we left off. Oh no, actually this is the theorem statement. And then we actually did this one as well. Right. So these are some ways to build. These are some ways to build new examples out of old examples. And again, and again, you can do other things as well. But you can there could be you can sort of combine these techniques clearly, right? You can do one and combine, and you'll get a lot of examples. But so now let's try to explain that assumption sort of very mild. So the first assumption guarantees continuous sample paths. Is sort of the minimal assumption that we know in the literature, which guarantees a condition in terms of the spectral measure. This sort of needs some. This sort of says, okay, your spectral measure decays that are not too far. Decays that are not too slow rate near infinity. And A2 says that your spectral measure is nice near zero. And we sort of think that this is necessary. And just to give one example, if you take a spectral measure of this form, A plus B cosine 1 over x on this compact set, then the exponent does not exist for some choice of A and B. So you need B larger than A to make sure that questions that I can answer. Okay, so let's see. So in this for this spectral measure, we know that so we can show that for some AB the exponents do not exist. We claim that for no AB the exponents exist, but that's something that we don't know at this point. And so just to expand a bit on the example, the last example was a compactly supported measure, and it's absolutely continuous. So there is no problem with A1 holding, right? Because it's compactly supported. The density is continuous everywhere except at zero. So this sort of demonstrates the special role of the origin, right? Discontinuity away from zero is fine. You can have as many discontinuities as you like. Here there's one, but you can have more. But discontinuity zero, you have to be more careful about. And like I said, we conjecture that the exponent never exists for any AB as opposed to some AB. Okay, so to continue our main results, the second main result sort of illustrates the special role of singular measures. So let's say mu is a measure which is nice near zero and infinity, and nu is measure which is nice near infinity. So nice near infinity means that it has log beta moment. Nice near zero will mean that mu prime zero exists. So these are the two assumptions. And you assume that nu prime zero is zero. So let's say you assume that nu is not supporting an interval around zero, but we can work with this. Then mu plus nu also has a limit. Mu plus nu is nice near 0 and nice near infinity, because you can take sums. And in this case, both the exponents exist by your first theorem, right? Because since mu is nice, this takes care of the, we cannot allow both of them to be 0, but we assume that mu prime 0 is positive. So the sum is positive. So the derivative of the sum is positive. And so what we know is that in general, sorry, I haven't assumed singularity so far. The singularity only comes in here. So in general, theta of mu plus nu is greater than or equal to theta of mu. So meaning it's easier for this process. So the one with the larger exponent, it's harder for them to persist. So this process is easier for this process to persist than compared to this one. And this equality happens if and only if mu is singular. So in some sense, if you add a singular measure whose nu prime 0 is 0, it doesn't change the exponent, right? That's but this is not true for non-singular measures. If you add a non-singular measure not supported near 0, this will change the exponent. And so, okay, so in particular, this applies to singular measures away from the origin, right? If your singular measure happens to not contain 0 in its support, let's say it's supported -1 to -infinity and 1 to infinity, your exponents will match. This allows to throw away singular parts. This sort of tells a bit about how we do the proof. We first remove the singular part away from the origin. Near the singular part, we cannot remove it. We sort of smooth it out by a continuous process. So essentially, our spectral any spectral measure, we can replace it by a spectral measure which just retains the absolutely continuous part away from the origin, and near the origin is sort of as a smooth version. And then we work with this spectral measure. So essentially, we can convert a mu which is not singular to a one which is singular, and then the other way around, we can convert a mu which is not singular to a mu which is singular, approximate by a mu which is singular. We can convert a mu which is singular by one which is not singular, and then proceed from there. So it's enough in some sense to study non-singular examples. And just to explain what can go wrong with singular examples, suppose and the special role of 0. So suppose I take nu to be a point mass at 0, right? So 0 is at 0 one has to be more careful. So if I take nu to be a point mass at 0, then the process is just x mu plus a single normal. Yes, sigma square is a mass that you put at 0. And this sign denotes that these two are independent. I'm going to use this sign sort of throughout the talk. And in this case, how do I make this persist? Well, if I want to make this persist, then one way to make this persist is to make sigma times e to be larger than some fixed but large k, and then just say that the rest I'm going to just bound it by the same k, right? So then the sum will be positive. And this quantity is free of t, right? This quantity has no t, so this doesn't impact exponent. So I'm thinking of here k fixed and k going to infinity after t going to infinity. So for a fixed k, this does not impact exponents. The whole contribution of the exponent will come from here. So I need to give a lower bound to this. So like I said, the first term is free of t and doesn't impact the exponent. Say for the other term, you can bound this quantity by this. You can just break this into blocks. This is like a Slepian type estimate except for the absolute value. And this is by the Hartree-Siddak inequality, which says that you can do it for any two blocks. So you can, if you have 0 to t plus s, and if you have absolute values here, you can go from 0 to t and t to t plus s, which I can replace by 0 to s if your process is stationary. But the Hartree-Siddak also applies to non-stationary Gaussian processes. Like I said, here we use stationarity in both. So in sort of simplifying what we get, we sort of use stationarity. But we can sort of bound this term by this. And now we have to, so now we want to argue that this term is very close to 1 for k large, right? Because here you have a compact interval, k is going to infinity, so this is very close to 1. And essentially, therefore, if you go back to the previous slide, so this is very close to 1, and this is sort of does not impact the exponent. So this is at the exponential scale, this is very close to 1. So this is like e power minus small ot. In fact, one can give much better rates if one wants to here. But so what we get is this lower bound, and this is e power minus small of t. Like I tried to explain, this is like a number close to 1 to the power t, and this does not impact the exponent. So in this case, if you add this mu, your exponent will change. Start with any mu that you like and add this mu. What you get is a measure which has exponent 0, right? And so we added a singular measure, but the problem was that it had a point mass at 0. So that's not allowed. So your mu prime 0 is 0. So just to explain what's the advantage if you don't have a mass at 0, let's take this example, which is point mass at 1 minus 1, half and a half. So in this case, the process is x mu plus this z1 plus z2. So this process independently we studied, but now there's an x mu added to it. All of these are independent. Z1 and Z2 are IID. And now the claim is that the persistence of this is close to the persistence of this, right? And so one direction is sort of easier. So I want to claim that, okay, so here this notation approximate with respect to t means that I'm allowed to commit errors which are e to the power small o of t, right? So I'm not going to track errors which are e power small o of t because that's not going to affect my exponent. So that's, and I'm just going to hide it using this notation. So the fact that this quantity is larger than this quantity sort of follows by a similar bound. So I just want this to persist. So one way to make this persist is to make Z1 and Z2 small enough, and then just bound this, and then just want the persistence of this, right? So if these two are less than delta and this is larger than delta, then the sum will be positive. And so now this quantity is again free of t, so this does not impact the exponent. And so all I need to care about is this term. And now this one, I should have put a mu here, by the way. There's a mu sitting here. So now the claim is that this process, the persistence at delta, for this process, the persistence at delta is close to the persistence at 0. If delta is, I'm thinking of delta going to 0 after t going to infinity. So it's not exactly small o of t, but this is like e to the power constant delta t. So we have very precise versions of these estimates in terms of delta and t and the spectral measure in our upcoming draft. But let me just sort of slightly abuse this notation and just say t. And this will allow me to change this to 0, and that's pretty much it, right? I mean, I know that the LHS is greater than roughly this quantity, and this is what I want. So basically I can drop this Z1 plus Z2. This part has no impact on the exponent, at least in one direction, right? The other direction is actually not that direct, and this is actually the non-trivial part, and it requires a log concavity of the Gaussian measure. And this this other direction works for all measures and does not require nu to be singular. It does require nu to not have a mass near 0, though. That's important. So more precisely, this is what we claim, that the persistence of mu plus nu is less than equal to the persistence of mu at a suitable, when you sort of allow for small errors for any nu with nu prime 0 equal to 0. And the proof of this I plan to sketch in the second half of the talk, but I'm not sure how much I can get into here, but I'll post my slides and I'm happy to take questions. So this is sort of why sort of 0 is special and singularity is also special. So one thing which we used in the sketch that I in the last two slides is continuity levels, and it seems like a reasonable thing to assume, but it's not that direct. So there does exist continuity of exponent results for Gaussian stationary processes. The best one that we know of prior to our work is this work of Li Shao, which applies to non-negative correlations which are strictly decreasing. In this case, we know that we know some sort of continuity in levels. So continuity levels meaning that persistence at delta is close to persistence at 0. So the chance that the process is larger than delta is close to the chance that the process is larger than 0. close being at an exponential scale. So one of the main things that we do, and this lemma is very useful throughout the paper, and I think this will be useful even going forward, is that is a change of level lemma just under A1 and A2. So we don't need non-negative correlations or decreasing correlations. And in particular, our result applies to any non-negative correlations. The only catch on any is that we need some sort of log beta moment assumptions. Whereas if I remember correctly, Li-Shao doesn't have any tail conditions on rho, so it doesn't have any. So they do assume non-negative correlations decreasing. I'm not sure whether that implies some sort of moment assumptions on the measure, but other than that, it sort of applies to. In particular, it applies to any integrable correlation. I think any integrable correlation will have a nice density. No. So we still need the log beta moment assumption, right? So the only the log beta moment assumption may not be the general part, but other than that, we sort of these are very mild conditions, as I tried to explain. And this is sort of one point where you see this assumption A1 again. I think I messed up here. They should be A2. The assumption A2 here. So mu prime 0 greater than 0 is needed. So in particular, mu prime 0 equal to 0. If you have mu prime 0 equal to 0, you will not have continuity levels. And okay, you will not have continuity levels is not I guess the claim. We have an example where mu prime 0 is 0 and continuity of levels is not true. And the example is the same one, right? The example is again half delta 1 and delta minus 1. In this case, mu prime 0 is 0 because you're not putting any mass near 0. In this case, this persistence probability is 0 if delta is greater than or equal to 0, and it's some positive constant if delta is negative. And so clearly your exponent is infinite if delta is greater than or equal to 0, and 0 if delta is negative. So if you change delta a bit, your exponents change a lot. You do not have this continuity. And so this is one of the reasons why A1 is required. So if you drop A1, you may not have continuity levels. But in some sense, it's not as bad, because in some sense, when mu prime 0 is 0, you expect the exponents to be infinite. So okay, so or infinite in one direction, right? So so maybe one should not ask for this type of continuity when mu prime 0 is 0, but it's not true. Okay, so let me try to expand a bit more on why singular measures are special. So most of our techniques go through this, go through study of small balls. So whenever we sort of want to study persistence of something, let's say mu, we say mu is, let's say, nu plus some small perturbation. We say persistence of mu is approximately persistence of mu plus a small ball of the perturbation, meaning, okay, so I'm writing x is y plus z. I'm saying if x has to persist, then y has to approximately persist at a closed level, and then the small process has to be less than delta throughout. And so we need sort of estimates of small ball type events. Well, the classical literature on small ball usually studies this for L going to 0, with t fixed. Here we are sort of considering t going to infinity first and then L going to 0. So it's slightly different, but still we use the term small ball to describe probabilities of events like this. And okay, so let's define the small ball exponent similar to Peirce's exponents. It's negative limit 1 over t. Okay, there's a log missing here. So log of the probability the supremum is less than L. And I can define this because unlike Peirce's exponents, the small ball exponents always exist, no matter what the mu is. You give me a mu, the small ball exponent exists. Well, I mean, I do need to be able to define continuity of sample path. So assume the log beta moment, but no assumptions on mu prime 0, no assumptions on niceness near 0. And this is because of the Khatri-Sidak inequality, right? This is sort of well known, or I don't know if the exponent is stated in this way in the literature, but it sort of follows immediately out of what is known, that you have this bound again by subadditivity, you have this exponent. And so one of our main results says that this exponent is 0 if and only if mu is singular, right? So this sort of explains why perturbations by small balls do not change the exponent, right? Because you sort of small ball the small perturbation. If it happens to be singular, it's not going to change your exponent at all. So as an illustration, let's take a recurring example. So mu, which is half delta 1 and delta. Okay, again, this is typo. This should be delta minus 1. Sorry of the typos. I'll fix the typos before I post the slides. Or at least I guess one version of slides are posted, but I'll sort of send an updated version. In this case, x mu is z1 cos t plus z2 sin t, same as before. Then your supremum is same as before. Then your exponent, this persistence happens always because now L is positive, not persistence. The small ball event happens always. Your exponent is always 0, right? So this is sort of captures the fact that for a small ball exponent, there is always 0. And now actually there's no need of a special care near 0. You can also do this if you have a point mass at 0. The general proof sort of involves more ideas. It sort of approximates a general singular measure as a combination of small OT many Gaussians in the discrete case, and then sort of as a chaining type argument to go to the continuous case. But in general, if you have small or many Gaussians, you can control the probabilities by estimates which are e to the small OT, and therefore the small ball exponent should be 0. And so, okay, this sort of tells you a bit into what, why small ball, why singular measures are special. The third result and the final result, or final main result that I'm going to discuss in this talk is the continuity of exponents. So continuity of exponents does hold under the following assumptions. So now I need uniform conditions of the nature that I demanded before. So mu k's are uniformly nice, meaning there's a beta independent of mu k's, such that the log beta moments are uniformly bound. So supremum is finite. And also mu k's are uniformly nice near 0. So now I don't actually allow for infinite exponents. So I say that mu k of minus xx divided by 2x is bounded between two numbers, which are, I mean, okay, I'm just, you can write these numbers in terms of the same alpha, doesn't matter. But these are uniformly bounded from 0 and infinity. So they're uniformly nice near 0. They're uniformly nice near infinity. These are the natural analogs of the conditions of the existence result. And now we need some sort of continuity results. The first one is sort of says that mu k converges to mu infinity in total variation. And the second one is that mu k prime 0 converges to mu infinity prime 0, right? So these have to exist. This is part of the assumption, and they converge. Right? So all of these are needed if you want continuity. Okay, these are sufficient conditions, but okay. So under these conditions, we prove convergence of, convergence of exponents. And we can sort of, we can combine some of the results that we already stated to sort of weaken this a bit. Some comments. We do demand that these are uniformly nice near 0 and infinity. Depending on the measures, this could be weakened a bit. The total variation measure distance, you can sort of do this after you remove the singular part away from the origin. You cannot remove the singular part near the origin, but away from the origin, you can remove the singular part, and you can sort of then say that total variation of this removed parts are close. That works, but it just makes the theorem statement a bit uncleaner. But you can, while applying it, you can sort of apply this. You can apply the removal first of the singular part and then apply this result. In particular, you don't need convergence of singular component away from the origin, but near the origin, you do need it. And using this, we can recover the continuity of exponent results for the non-negative correlations obtained in this result. Of course, this result goes beyond. There is a version of this result which goes beyond the stationary case, whereas the current work that I'm discussing only works with stationary processes. So that's a difference. But in the stationary case, we can recover this result again up to this log beta moment type assumptions. And so this is sort of a summary of the results. I'm happy to take questions. If not, I'm slowly going to go into the proof technique of proof techniques involved in our papers. Okay, so let's sort of break down the proof technique into a few steps. The first step, which is sort of, I guess, okay. So I mean, this is sort of a natural way to go, I guess. First, we start with functions which are very nice. So by nice, I mean C2 functions, and it's compactly supported. So the thing doesn't qualify because it's not C2 at the end. It's not C2 on the endpoints, but I want C2 everywhere. So we want to understand the exponents, existence of exponents in this case, and then hopefully we can approximate measures which are which have densities by nice continuous functions. And finally, the hope is that we can approximate general measures by absolutely continuous measures. The last part I'm not going to sketch, but sort of the idea is that you remove the singular part away from the origin. Near the origin, you sort of smooth out the singular part to get a non-singular part, and then you sort of approximate it. But in this talk, I'm only going to focus on the first two parts, meaning how to do it with densities. This will cover the sync process example. And so, as is well known, you can differentiate twice, and you can express the correlations. Again, I'm utilizing the connections between the correlations and the spectral measure to express the correlation in terms of this. If your f is nice, you cannot do this if f is not nice. But if f is so if f is twice differentiable, you can do this, and you get this easy bound, which is that the correlation decays like constant over t squared. In particular, the correlation is uniformly integrable. And so the type of techniques that was used in a paper with Amir is also relevant here. And sort of let me sort of roughly go over the proof technique in this case. So the idea is that you start with the interval 0t, and you fix m and delta, and you take intervals of size m, so m being large and delta being small, but the order of limits is that t goes to infinity first, followed by m, followed by delta goes to 0. Same also goes to infinity, delta goes to 0. And then you leave out small gaps of delta m, right? So you sort of keep m and you leave out small gaps of delta m. And so how many intervals do you get? You get t over m times 1 plus delta many intervals. I'm just going to assume that these are integers. And so call these intervals ii. And so, okay, so if I want the process to persist on the whole interval, then an upper bound is that the process to persist on these blocks, right? I'm going to just throw away the intermediate blocks of size delta m. I'm only going to gain in probability, and the hope is that I don't lose too much here, because what I'm leaving out is small compared to what I'm keeping. And this is sort of the key step which I'm not explaining here, but this is sort of where we use this fast decay of correlations and the fact that we leave out reasonably big gaps. The gaps are still delta m, and this sort of this step was done for non-negative correlations in my paper with Amir, but this sort of we repeat. So this particular part, you don't need non-negative correlations. You only need the bound to be non-negative. You don't need the starting one to be non-negative. We sort of use that. We sort of repeat this this proof idea here, and sort of we can do this in an approximate sense, where the errors depend on m, but we can track the errors. But once we can do that, if you believe me on this step, then everything else is fine, because now you have each of these, you have a stationary process is just going to be 0m to the n, right? And persistence on 0m to the n. And now you can have an approximate. So now we are going to take 1 over t log, right? So and this you will get 1 over t log pt is less than or equal to 1 over m 1 plus delta log pm plus some error which depends on m. You get the m times 1 plus delta because n was t over m times 1 plus delta. And now you first let t goes to infinity, followed by m goes to infinity, right? So if you take a lim sup as t goes to infinity, this part remains unchanged. You get this. If you take a limit over m, limit over m, you get this, and this term goes away. And once you see this, you are done, because delta is arbitrary, and now I have lim sup less than or equal to lim. So there is an exponent, right? So this is sort of the rough idea of what goes on in the case where you have fast decaying correlations, fast meaning integrable, or polynomial integrable. We don't need we didn't need it to be t squared, but we do need to be t to the 1 plus delta. But okay, I mean we can get it to be t squared. And so that completes the proof in the fast ticking case. So now let's just indicate what's going on for general densities. So let's take mu to be absolutely continuous with respect to Lebesgue measure, and let f be the density, and it's not smooth. But you do need mu prime 0 to exist, so it does put some conditions, and this covers the same process. You just take f to be an indicator, and I can approximate f by g, which is a C2 function on a compact set, because since f is integrable, you can sort of throw away the tails, such that this g is close to f in L1, and also g at 0 is close to f at 0. I need to do this. I mean, this is sort of important because of the special role of 0. But once I get a g like this, then the claim is that the persistence are compatible. This is sort of course, a big claim. And so this, I'm going to take nu to be the measure induced by g. And once we get this claim, if I know that I already know that this one has an exponent, so this one will have an exponent. And I'll sketch this claim. Let me see how much time I have left. I still think I have 15 minutes left. Okay, so let me sketch this claim, at least one of the bounds, the upper bound, which should be shorter. And I'll assume that nu is greater than or equal to mu, right? So this sort of makes the sketch a bit simpler, but it also gives an overview of the type of things that we use. And because of this non-symmetric assumption, you will see that the proof of the upper and the lower bounds will be very different. In general, both the upper and the lower bounds go into, in general, there's no upper and lower bound, right? Because in general, you have to show, okay, I mean, in general, this claim is symmetric, but this sort of assumption makes it not symmetric. In general, if you don't have this, you sort of go from mu to nu to a common larger one and then go down, right? That's sort of, you go up and then you come back. But let me sort of just assume that mu is larger than nu in this sketch. So we want to say that the persistence of mu is less than or equal to persistence of nu. And so now you'll see the assumption that nu larger than mu being used. So since nu is larger than mu, we can write nu is mu plus sigma, where sigma is a measure, right? Because sigma is non-negative, it's countably additive because each of them are countably additive. So it's a measure. Both of them are finite measures. And therefore, I can do this decomposition. I can write the process with spectral measure nu as the process with spectral measure nu plus an independent process with spectral measure sigma. And this decomposition helps out a lot. Once I have this decomposition, if I want this to persist, so I want this quantity is this one. So these two are the same. The right hand side here is the left hand side here. If I want this to persist, then it's enough for this process to the mu process to persist, and then the supposedly small process to be smaller than delta, right? I mean, if I have these two, then this will happen. Now I just need to estimate these two quantities. So let's just do that. The first term, so the second term, sorry, the second term with sigma, I can get a lower bound to that, to just going to the interval 0, 1 and then make it equal to the t. Again, I'm treating the t as an integer, but that's sort of fine. And therefore, one needs to show two things. I need to show that this term doesn't affect the exponent. So basically, I need to show that this term is very close to 1. So this term is very close to 1. And also I can do a change of level, right? I mean, this one we already know, right? So the first one sort of follows because this measure sigma is small in total variation. So so therefore you have a process on a compact interval, and the variance of the process is uniformly small. Therefore, the suprema is small. You can do this by standard estimates. For example, you can use Borel-Tist to do this. So this sort of immediately says that this term is very close to 1. This goes to 0 actually if you take the approximations going to 0. This random variable. And the second one, as I tried to explain, is the change of level. And that's sort of what's going on for the upper bound. Now, what happens for the lower bound? And somehow, as I tried to explain, the proof here is very different. We need to show that persistence of mu is larger than persistence of nu, but now nu is the larger measure as before. So just to sort of reiterate what you may have already noticed, we only used the fact that sigma is small in total variation in the upper bound proof. We never used that mu prime 0 is close to mu prime 0. And this will be used in the lower bound, of course, otherwise, the conclusion is not true. And so in particular, this assumption tells you that sigma prime 0 is close to 0 because the difference of these two are close. And I'm going to work here under the slightly stronger assumption that sigma has no support on minus AA. In general, we can make the weaker assumption work, but let's take the assumption that sigma sort of vanishes on a small interval around the origin. Then the two measures agree on an interval on this interval, and therefore, okay. So let's take this function h, which is a triangle function, which has height 1, with supported on minus AA. With this definition, if you look at, so h vanishes outside minus AA, so does h squared. So h squared sigma is identically 0, right? Because h vanishes outside this interval and sigma vanishes within this interval. So h squared sigma is identically 0. And then what we want to show is this inequality. So just to explain, this equality is, so only the red one is what we want to show. These two are immediate. Why? Because mu is same as mu plus h square sigma, because h square sigma is 0. So these two are same. And mu plus sigma by definition is new. That's the way we define sigma. And so this is also immediate from the definition. But this is the claim. Mu plus h square sigma is larger in persistence than mu plus sigma. And this we claim much more generally. We claim that this holds for the general measures mu, sigma, and h, of course, under some assumptions, which I'll try to indicate. And so for verifying this claim, what one has to note is that this h square sigma is a spectral measure of this process. You take this x sigma process. This is the Gaussian stationary process with sigma as the spectral measure. You convolve with this function h, capital H, which is a Fourier of small h, right? Which is given by this function, which is nice and integrable, because that part is important for the proof. But okay, so that's you take this function. It's sort of not too slow decaying. It's sort of fast enough decaying for our purposes. That will also be important in the sketch that I'm going to present in the next slide. But so essentially this part, I can write the Gaussian process like this. And so let me first indicate what's going on for mu equal to 0, which is sort of easier. In this case, you just have to show this. And what I'm claiming is just this, right? So I am claiming that the persistence of this convolved process is larger than the persistence of this process. And this is sort of immediate, because what I'm demanding is that if this function is non-negative, then if I convolve it with a non-negative function, this is non-negative. It's immediate, right? Because non-negative function convolved is non-negative. There's nothing to show. Maybe there's not even an estimate, right? Okay, that's that. Well, there's a slight catch. Well, this event here just demands non-negativity on 0t. And maybe while doing this integral, we go a bit outside 0t, right? So that's possible. And so to make this work, we sort of, let's assume that H is compact support. In general, the H on the last slide is not compactly supported, but then we proceed via truncation and we show that, the truncation can be controlled by a Borel test. But okay, so now H is a compact support. So even though it affects points, even though points outside this interval affects these quantities, affects this value, you don't need to go too much outside. So essentially, if you demand that your process is non-negative on a slightly bigger interval, so this sort of captures all the points that can come up here, then this happens, right? So you don't exactly get 0t, but you sort of expand it a bit, and that's fine. I mean, it's not too much, right? Compared to 0t, it's not too much. And what you get is persistence on a square sigma is comparable to persistence of t plus 2l with sigma, right? And it's an exact inequality. There's no loss here. If you have compact support and mu equal to 0, if you don't have mu equal to 0, then things are a bit more tricky. Here you have to use this log concavity of Gaussian measure, and also the fact that H behaves like a probability distribution. So this log concavity gives that log of this probability, that infimum, of this x mu process plus a perturbation of this form. It can be any function. It doesn't need to be vt minus s. It could be a bivariate function of t comma x. But I'm just taking it to be vt minus s because that's what I'm going to plug it by eventually. So take any function v, and then you can sort of weight it by h outside, and that's going to be less than equal to weighing it inside. That's by log concavity of the Gaussian measure. And now I want to give a lower bound to this quantity, which is similar to what I did on the last slide. So I can replace this t by t minus s because of stationarity. I can sort of do a change in level, and therefore I can reparameterize t minus s, and this quantity I can lower bound. So to make this persist, it's enough to demand that this process persists on a slightly bigger interval, similar to what I did on the last slide. Now this quantity is free of hs, so I can take this outside. So I have this as a lower bound to the left hand side, and this is my upper bound. And now I can cancel the two logs. So I have this quantity less than this quantity, and this is pretty much it. I mean, I'm comparing two persistence probabilities with varying functions. Now I'm going to plug. Okay, so this is okay. Now I'm going to plug v to be x sigma, which is a perturbation, and take another expectation. So I get a conditional version and take an expectation over x sigma. This is what I get, and this is what we want, right? And again, this is an exact equality if your capital H is compactly supported. The Fourier of H is compactly supported, but our H is not compactly supported. But it's fast enough decaying that we can do this by truncation, and we get an approximate version of this. And this sort of captures captures a lower bound. And let's sort of state some interesting conclusions, or not conclusions, so as to say, I guess, byproducts of the proof technique. So what we get out of this is something of this nature. Suppose mu and sigma spectral measures which are nice near 0 and infinity. In fact, you don't need sigma to be nice near 0. You just need mu plus sigma to be nice near 0. But let's sort of keep this assumption for now. And h be a non-negative function which is 0 at 1. And your h hat, suppose your Fourier is non-negative and it satisfies some mild decay conditions, then I can do this comparison, right? So then one can do this comparison. In particular, if you take nu to be, so in particular, you take a measure nu, arbitrary, and take mu to be its truncated measure and sigma to be the measure minus its truncation. So this is supposed to be small if L is large, small in total variation. Then take h to be this function, the same function on a bigger interval. Then the exponent of nu truncated to minus LL. This is just the exponent of mu. That's the definition here. Now this is nu plus a square sigma, because a square sigma is 0. This is less than theta of nu plus sigma. This is by this lemma. This is equal to theta nu. And so if you just forget what's in the middle, what I'm saying is that the truncated, so take a measure and take its truncation. The truncated measure has a smaller exponent than the original measure. And this is true for any measure, right? I mean, that's, and you can play around with this h, and you can plug in other h's, whatever h's you like. But this sort of is a comparison type inequality. And the final thing that I want to sort of comment is why singular measures don't change exponent. Okay, so suppose mu is nice near 0 and infinity, and sigma is a singular measure which is supported not at 0. Again, 0 is special. Then the one direction is okay. So x mu plus sigma. So this is the process that you get if you start with a spectral measure which is mu plus sigma. One way to make this persist is to make this persist and this bounded. And we now use the fact that for a singular measure the small ball exponent is sort of 0. So this probability is very close to 1 at an exponential scale. So this quantity does not affect your exponent, and you change the levels here, and that way you get one direction, right? So this is true. Here we use the singularity. Here we don't use the niceness near 0. Right, so in this direction you use singularity, but you don't use niceness near 0. For the other, sorry, this gives the exponents in the exponents become reversed because of the negative sign. In the other direction, suppose sigma is supported, suppose so sigma is supported outside minus AA. Well, not exactly. So, oh, actually, this is what we assume. So that's so we can do this even if sigma prime 0 is 0. But okay. Then you take the same function h, basically use the comparison lemma, then you get the other inequality. That's it. So the other one requires special treatment of 0, but does not require singularity. So one direction requires singularity, the other direction requires special, the special property of mu prime 0 equal to 0, and combining you have this, and that's that. And we show that equality does not hold if the sigma is not singular, right? So that one the first direction does not hold, equality does not hold if sigma is not singular. So this equality actually only holds for singular sigma. So let's sort of wrap up. So in this talk, we discuss a general set of tools for proving existence and studying properties of Gaussian stationary processes, which in particular does not require your process to be non-negative correlations, and sort of recovers most of the results known for non-negative correlations under very mild assumptions. We show that, in particular, we show that the exponents exists if your mu prime 0 is not 0 and not infinity, and if you have log beta moments, and we also give conditions for we also give conditions to demonstrate that, we also give examples to demonstrate that you do need the conditions for existence of exponent. So we study continuity of this exponent in terms of this metric, which is the total variation of mu and nu, plus this mu prime 0 plus nu prime 0. Right? You also need convergence of these values, and we show that this small ball exponent is 0 if and only if nu is singular. This we feel is an important result, and is of course used a lot in our proofs as well. And using this, as I explained, we show that the persistent exponent does not change if you add a singular measure which is not supported at the origin. So what are some things that one can try to think about? What are the things that remain open? One is, what is the exponent theta mu? In some special cases we have some guesses, but in general, if you give me a mu, then I guess the answer is that we don't know. We have no guess as to what mu is in terms of the, is there a nice formula in terms of the mu? Most likely there isn't, but okay, so that's a question. And the second one is, in this talk we focused mostly on the case where mu prime 0 is between 0 and infinity. What happens if mu prime 0 is equal to 0 or equal to infinity? We know that the exponent becomes 0 and infinity under very mild assumptions, and we also have rates in this paper. But maybe there's an exponent there at a different scale. Who knows? And maybe if you divide by t to the alpha log t, there's an exponent, or t log t, there's an exponent. But we are not close to proving this, anything close to this. Right now, we only have upper and lower bounds which match in a wide setting, but not up to constants. And another thing is, okay, can we say something about non-stationary Gaussian processes? Now, one disadvantage of the spectral measure is, of course, okay, or at least I do not know how to think of what is the analog of spectral measure for non-stationary Gaussian processes. Maybe correlation function is the way to go. We are not sure. We do have some results in terms of correlation functions for non-stationary processes if your process are non-negative correlations, but not in general. And the final question that one can study, actually, one can study a lot more questions, but one more interesting question seems to be, okay, so we know what is the exponent. Can we say something about how the Gaussian stationary process looks like if you conditioned on persistence? And there's a lot of ways to make sense of this question. We can try to look at the empirical process, or we can like to look at the endpoints, or we can try to look at finite dimensional marginals of the conditional process. But in general, what can we say about this condition process? I believe the empirical process we may be able to say something, but this is not work in progress at this point, but it's something that we plan to think about in the future. So with that, I'd like to end the talk, and thank you all for your attention. I'm happy to take any questions.